Right, they all sort of have the same idea, right? So we know that there's reflection symmetry, right? If they're even, if it has even symmetry, it's reflection in the y-axis. If it's odd, it has rotational symmetry, which is if you rotate 180 degrees about the origin, it's symmetric. We also have what's called translational symmetry, right? Because we know that trig functions have periods. Right, and therefore there should be a repetition, or there could be a repetition in the graph. So let's just start with that. Just if f of x plus p is equal to f of x for all x in the domain, where p is a positive constant, then f is periodic. I'll say f is, so f is a periodic function. And the smallest value of p is called the period. So, I mean, at its simplest, just think about y equals sine x, right? And it's periodic with a period of 2 pi, and tan x is periodic with a period of pi, right? So if we sketch one period, then we can sketch the whole thing, right? Simply by translating that one period over and over and over in both directions. And so that's called a translational symmetry, right? So in other words, we can figure out the period of the trig function we're sketching, then we really only need to work on one period of it, and then we can simply translate that over, right? Just like with rotational symmetry, you can just work to the right and then rotate 180 degrees about to sketch the left-hand part, or with reflection symmetry, you can sketch the right-hand side and then reflect that to the left-hand side. Okay. Small side period, P is period, for example. Okay, so if we know P and we can use translation, we can just sketch a particular period and then use that to translate. Or we may only be asked to sketch it on a particular interval, right? And perhaps that interval is 0 to 2 pi, and we look at it and we go, oh, it's got a period of 2 pi, so if I wanted the whole graph, I can just translate that over, right? So a question may restrict the domain and just say, hey, just sketch the graph on this particular domain. And if you're doing that, then you're going to use that information when you're looking for zeros and stuff like that, and just say, oh, well, I only need this value, right? Or I only need these values, because I'm just looking at a particular interval. Okay, so that's just sort of basic thing about trig functions. They're periodic and blah, blah. So let's sketch one. Sketch. Okay, so let's sketch cos x over 2 plus sine x. Okay, so look at that. Let's figure it out. So I'm going to do the A, B, C, D, E, F, G, H, right? On the test, we're going to step you through it. You know, do this, do this, do that. I don't know if it's exactly A, B, C, D, E, F, G, H, but it's going to be the similar stuff, right? So we're not asking you to have memorized the procedure. We're asking you simply to, you know, answer the sub-questions involved. Wherein, again, as we said, we're going to give you the derivative so that we are marking the same thing from everybody, not having to worry about, oh, well, if the derivative really was that, then, okay, because don't want to do that. Okay. All right. Anyways, so A is the domain. And the domain of this is x belongs to the reals, right? Because I cannot make 2 plus sine x equal to 0, right? I mean, sine x, lowest that could be is -1, so, right? What else? Intercepts. So the y-intercept, what do? We set x equal to 0, which gives me cos 0 over 2 plus sine 0. I don't know, I put a theta there. The cos of 0 is 1, and the sine of 0 is 0, and so we get 1/2. Right? 1/2. 1 over 2. X-intercepts. Well, to get the x-intercept, then we need cos x to be 0, right? I mean, 2 plus sine x is just whatever it is, right? So when cos x is 0, so cos x equals 0. And we know that, right? Go back to last semester or last year. X is pi over 2 plus n pi, where n belongs to the integers. Now you might see this expressed differently, right? So I'm just going to show you a couple of ways, because you know, we could factor out the pi over 2. Gives me 1 plus 2n, right? Yep. Which, you know, could also be written as 2n plus 1 times pi over 2. Right? So they're all the same, right? They're all the same, just different forms, right? So they're just, yeah, I mean, if you see it expressed in this form, you're actually go, huh? You know, you say, oh, right, okay. It's just a variation of this. Okay, so be aware of that. Symmetry. So what can we say about symmetry? Well, it's not odd and it's not even. Okay, you can just by observation you can kind of see that, right? So F is neither odd nor even. But since it's based on sine and cos, it has a period of 2 pi, right? It has a period of 2 pi. So there is translational symmetry. But has a period of 2 pi. So we will graph on the interval 0 to 2 pi, right? And then if we need more, we'll just repeat. Whatever we drew, we'll just draw to the left, and we'll draw to the right, and that's our whole graph, right? So we're going to take that chunk, and just like sine theta, right? I mean, that chunk 0 to 2 pi is one complete split, and we just take it, paste it over there, and over there, and over there. So we could do that here as well, right? So we can limit ourselves to doing the interval 0 to 2 pi, because that's one complete period, and then graph that. Asymptotes. There are none. Okay, so there are no, there's no way for 2 plus sine x to be equal to 0. Right? And then we've got this periodic function, so it's not going to approach a value, right? It's always going to just be repeating some sort of a period, which is 2 pi. Okay, now the fun stuff, right? Intervals of increase, decrease. So that requires us to find the first derivative, right? Which on the test we're going to give you. We're just going to say, show us that this is the first derivative, right? In other words, show me the work that gets you this as the answer. All right, so, well, it's a quotient times so it's the numerator times the derivative of the denominator, which will be minus sine x, minus the denominator, which was cos x, times the derivative of the denominator, which is cos x, over the denominator squared. Right, and then we're going to attempt to simplify that. So you can see, I'm going to end up with like a minus sine squared x minus cos squared x, and if that was sine squared x plus cos squared x, it's 1. So, okay, let's play with that. So we got minus 2 sine x minus sine squared x minus cos squared x Okay, now it's at that point I say, hey, if I can make that sine squared plus cos squared, in other words, if I can get rid of that negative sign in here, which I can do by throwing it out front and going 2 sine x plus sine squared x plus cos squared x over 2 plus sine x all squared, which gives me negative 2 sine x plus 1 over 2 plus sine x squared. Okay. And there's all the details, right? All the details. So we're going to give you that. You're going to have to just show that work, right? I mean, this isn't the problem you're going to get. At least I don't think it is. But you get some similar problem and you show the work. All right. So intervals of increase and decrease require us to find out when is this positive, when is this negative, right? So we look at this and we say, well, that's always positive, right? Because whatever it is, I'm squaring it. Even if this weren't always positive anyways, which 2 plus sine x is always positive anyways, right? This lowest value for sine x is negative 1, so that's at its lowest 1 and at its highest 3, but then it's being squared anyway, so ignore all of that and just say it's something squared, therefore it's positive. This expression here is the negative of this, so when 2 sine x plus 1 is negative, then that will become positive and we'll have an interval of increase. But let's work our way through this. So let's just start with this. Since Okay, so I want f prime of x to be greater than 0. Those will be my intervals of increase. That's going to happen when the negative of 2 sine x plus 1 is greater than 0. Which means that 2 sine x plus 1 has to be less than 0, right? Because you're taking a negative of a negative. Or just multiply both sides by negative 1. It's going to reverse the inequality, right? So 2 sine x is less than negative 1, and sine x is less than negative 1/2. And that happens, you gotta know a little trig here, right? I mean, strictly less than. So sine x will be less than negative a half from 7 pi over 6 to 11 pi over 6, right? And I don't know how you want to. You could do this. Say there's negative 1/2, and then kind of figure out that this is 7 pi over 6, right? Like and use your, whatever you did in 30-1. I would use reference angle. So, okay, when is sine x a half? So first I'd say it's in quadrant 3 and 4, right? That's where sine is negative. It's quadrant 3 and 4. The reference angle for a half is pi over 6, so I need an angle of pi over 6 in quadrant 3, which is 7 pi over 6, and quadrant 4, which is 11 pi over 6. So this here is 7 pi over 6, and this here is 11. And that's what will be less than negative half in that interval, right? So that's when we're going to be increasing, right? So f is increasing on the interval 7 pi over 6 to 11 pi over 6, and decreasing, right? Because when this is positive, then that negative is going to make it negative, right? And it'll be decreasing everywhere else, right? Which is 0 to 7 pi over 6 and 11 pi over 6. So 0 to 7 pi over 6 and 11 pi over 6 to 2 pi. Okay? Keeping in mind that we are now restricting ourselves to the interval 0 to 2 pi, right? Since we know the period of this function is 2 pi, then we can restrict ourselves to the interval 0 to 2 pi, and then use this translational property to, simply sketch more. Okay. Or we may just have been asked to sketch it on the interval 0 to 2 pi. So when you're doing the questions, you got to look. It may just say, just do it on this interval. Now, what does all that mean? Well, if we are changing from decreasing to increasing, then what do we have? A local minimum, and then when we're changing, so there's going to be a local minimum as we go from decrease at 7 pi over 6, and then we're going to change from increasing to decreasing, giving a local maximum at 11 pi over 6, right? So, there's a lot of so's. Well, whatever. Oh wait, that's f, which is local max and min. So we say from part E and the first derivative test, we could use the second derivative test, but we haven't got it yet, right? And it's always the poor cousin, seems to be like, you can use it to find if it's a max or a min, but you already figured it out. So we have a local minimum. So that's the cosine of 7 pi over 6 over 2 plus the sine of 7 pi over 6. The cosine of 7 pi over 6, where is that? That's quadrant 3. Cosine is negative, so it's going to be negative root 3 over 2. Over 2, and we already know that's minus a half, right? Because that's where we figured out that, hey, here's where the minus a halves are. So that's going to be 3/2, so 2/3. Okay, so a local min at 0. 7 pi over 6, negative root 3 over 3. Okay, let's say that, local min. So I'm going to have to extend this a bit. And we know there's a local max when x is 11 pi over 6. Let's cut to the chase. So the cos of 11 pi over 6 is the same as the cos of 7 pi over 6, only it's positive. Right? I mean, it's in the same position, has the same reference angle, it's just a positive value. And so what do we got? Local max, 11 pi over 6, and root 3 over 3. All right, so we know when it's increasing, right? It's going up. When it's decreasing, when it's going down, its local maxes and mins. Kind of decreases as it goes to the min, and increases as it goes to the max, and decreases as it comes away from the max. So, you know, in a sense, when you plot the local maxes and mins, you sort of know where it's increasing and decreasing. Okay. But now we need to have concavity and points of inflection. And for that, we need the second derivative. But I'll let you finish getting this down. Okay. That's G, concavity and points of inflection. All right, for that, we need the second derivative. So it's the denominator of the first derivative, 2 plus sine x, all squared, times the derivative of the numerator, which is, of the first derivative, which is minus 2 cos x, minus, only it's minus and negative, so we're going to go with plus. 2 sine x plus 1, which was the original numerator, times the derivative of the denominator, which is going to be 2 times 2 plus sine x times the derivative of the inner function, right, which is cos x, over the denominator squared. Okay, now your job is to simplify that, right? Because you're going to know the answer on Thursday, right? We're going to give it to you, but you've got to simplify this so that it actually is what we says it is. So let's look for a common. What do we have? So I got a negative 2 cos x, and I got a 2 cos x, and I've got the 2 plus sine x. So let's go with 2 cosine x, and let's go with 2 plus sine x. Okay, so here we're going to get a 2 plus sine x, because we need one of those, and it'd be a negative. So negative 2 plus sine x. Okay, so the negative 2 cos x, I got the 2 cos x, I need the negative. I got the 2 plus sine x, I got one of them, I need another one in here. Plus, I've got the 2 cos x and this, so all of this is gone, and we're just left with 2 sine x plus 1. And, you know, let's just throw that in brackets for the heck of it. Equals. All right, let's do a bunch of stuff at once. Am I missing a 2? I got a 2 cos x, so that's out here. And I've got the 2 plus sine x. No. Yeah, you really got to be careful with. Luckily, you know where you're going. Right, at least on the test, you know, we know where we have to end up. Let's just make sure. Let's see if we can actually get there. It's usually it's not that. Well, no, I'm not going to say that. Sometimes it is really hard to figure out how the heck do I get that? You know, but we know in doing second derivatives with quotient rule, you know stuff's going to cancel out, right? Like this is going to take the fourth power down to a third power, right? That. So let's just start with the 2 cos x. Let's go with the 2 plus sine x cubed. And let's see what we get here. So I get negative 2 plus sine x, or minus sine x, plus 2 sine x. So I've got a minus sine x plus 2 sine x will be plus 1 sine x, right? So sine x. And I've got negative 2 plus 1, which is negative 1. So I get a sine x minus 1. Now, it could be written in another form, so let me just show you, hey, here's an alternate form. So just in case we say that, it's something different, like you're looking for, maybe we say it's this. What if I put a negative out front, make that a 2 cos x? Then I'm going to have to flip these signs, right, to get that negative out front. So I'm going to go 1 minus sine x over 2 plus sine x cubed. Okay, so it's possible we say it's this, and this is where you're at. You just got to realize, oh, let's take a negative out of here, stick it in front, and it's all good. Okay. So why? I mean, sometimes you're not as far from the answer as you think, right? Like you think, oh, God, I can't, but it really is just, oh, let's take a negative sign out, or let's do some simple thing. Okay, so what about this second derivative? Okay, 2 plus sine x cubed is always positive, right? And well, because sine x at its lowest is negative 1, so at its lowest 2 plus sine x is 1, so this is always positive, right? So instead we're worried about what's up here, or what's here, either way. Okay, so let's say that. 2 plus sine x quantity cubed is greater than 0 for all x. And sine x minus 1 is less than or equal to 0. So think about it. The largest value for sine x is 1, right? So if I'm subtracting 1 from it, I'll get 0. Otherwise, it's going to be less than 0. Okay? So sine x minus 1 is less than or equal to 0 for all x. All right, so let's go back here. So this is always positive, this is always 0 or negative, so the sign, this is always positive, this is always 0 or negative, so the sign of this depends really on cos x, right? If cos x is positive, and that's always negative, we're going to get a negative. If cos x is negative, and that's always negative, we're going to get a positive, because that's always positive. So we're not ignoring this. Okay? So for our second derivative then, we are going to say then f double prime of x is greater than 0 when cos x is less than 0, right? So when the cosine is negative, the other expression up top is always negative, or 0, but we're looking for negatives here. Okay. And the negative times a negative will give you a positive. So f double prime of x. So we think about what the cosine function looks like, and we say this will be concave up. When cosine is less than 0, that's going to be from pi over 2 to 3 pi over 2, right? Again, however you figure out your stuff. So from pi over 2 to 3 pi over 2. Otherwise, the cosine function is positive, right? 0 to pi over 2 or 3 pi over 2 to 2 pi, which makes the expression negative, so it'll be concave down. So f double prime of x is concave down. From 0 to pi over 2. And from 3 pi over 2 to 2 pi. See, this is when it's handy to have a partner, right? Because you got somebody to kick around the ideas off of, right? Somebody to say, wait a sec, And I always figure this: if you can if you can work with a partner and get one more mark than you could on your own, it's kind of worth it, isn't it? Because you're going to score higher. So if you know nothing and you know nothing, then don't ask for a partner. If you just say whatever, I'm just going to drag somebody down with me. I don't want to do that. Even so, still take a partner. Right? Because their mark's going to be similar to yours anyways, but if you sat there and just said, I did no work on this unit, I know nothing, you might not want to take a partner. But Still, again, if you can help them get one more mark than they would have, they'll still say it's worth it, right? Okay, we got a mark more than I would have on my own. All right, so if we're going from concave up to concave down, then there must be an inflection point, right? So there's going to be an inflection point. Well, sorry, if we're going from concave down to concave up, there's an inflection point at pi over 2, and there's a second inflection point at 3 pi over 2. And the values there are zeros, right? I mean, pi over 2 is 0, the cos of pi over 2 is 0, and that whole expression becomes 0. So we have inflection points. We're almost done. At pi over 2, 0. And 3 pi over 2, 0. All right, so we got everything we need. Got everything we need to sketch this. So let's sketch this. H, sketch. So I'm mostly interested in just doing 0 to 2 pi, right? We know that otherwise we can just translate it over. So what are we going to do? Pi over 2. Pi. Messed up. 2 pi. All right. Now, let me go back. This whole 3 sheets worth of stuff, right? There's 3 sheets worth of info. I have 3 sheets anyway. So I have 3 sheets worth of info. Where I have intercepts. I've got 0, 1/2. Okay, so here, let's say that's 1. Okay, so that's my whatever y-intercept. My x-intercept occurs at cos x is equal to 0, so it's pi over 2 plus n pi. Okay, so there's my x-intercepts at pi over 2 and 3 pi over 2. Okay, what else? Increase and decrease is kind of obvious once you've got the max and the min, so let's put the max and the min in there. So the max is 7 pi over 6. 7 pi, how many pi over 6? That's 6 pi over 6, so 7 pi over 6 is going to be a little bit over here. 7 pi over 6 and negative root 3 over 3. What's root 3? It's like 1.7 divided by 3. Let's call it around a half-ish. A little more than a half, negative a half, I guess. So, go here. And I got a max at 11 pi over 6. That's 12 pi over 6, right? And multiply top and bottom by 6. So it'll be just short of this and a little bit over a half. Okay, now what else? We're concave up on this wait, so we had inflection. Oh, these are our inflection points as well, right? So we're concave down on 3 pi over 2 to 2 pi, so that's coming down. We're concave up on pi, so that's, you know, there's obviously areas of increase and decrease, right? And then this just kind of is going to go back up this way. And I think that's it. Okay, now, so let's verify that that kind of matches, right? So I'm going back. So it's increasing from 7 pi over 6 to 11 pi over 6. Okay, yeah. It's decreasing from 11 pi over 6 to 2 pi. Okay, decreasing, yeah. And it's decreasing from 0 to 7 pi over 6. So that's decreasing, increasing, decreasing. So that matches, right? Concave up, pi over 2 to 3 pi over 2. That's point of inflection. Concave down, yep. So I think that's it. So let's just take a look. I just say that. All right, so this was pre-graphed earlier, but you know, the nice thing about this is it even shows you with pi's, right? Like you can hit the max and the min. So decimals, put a little dot there, and then when you press on it, it'll show you. So 11 pi over 6, 0.5774. I'm guessing that's root 3 over 3. We got 3 pi over 2 and pi over 2. Those are our x-intercepts as well as our points of inflection. We've got 0 and 0.5. You can see how it's periodic. Okay, that's repeating there. And we got the max, we got the min. You don't have this on the test, unfortunately, so it's not like you can verify it, but you can walk out of the test with what does it look like? Okay, so that's a trig, right? Nice, not so easy trig because quotient rule and all kinds of stuff, right? So, you know, maybe you get easy stuff like x sine x or something, right? That's got to be easier. It's just product.